Hey everybody, this problem is from the Philpot book, and what we're going to do on this one is look at this beam, and notice we've got the two moments. They have magnitude of 375 Newton meters, and cross-sectional dimensions are shown, and what we're going to do is we're going to find several things. We're going to find centroid, moment of inertia about the z-axis, section modulus, and then we're going to figure out some stresses. All right, in parts B and C. So this is basically a problem about bending or design of beams. That's usually the chapter this type of material is in. So let's go over this one. And it's actually not too bad of a problem. It's kind of long though, because we got to find the centroid moment of inertia. So let's do those first. And obviously this is a composite body problem. So I always make the little table up to do the centroid and the moment of inertia, especially when I'm teaching, because I think it's a little bit easier for everybody to follow. All right, and I'm going to look at each one of these regions separately. I know there are different ways to calculate the centroid. Might be a little bit shorter, but that's just the way I'm going to do it on here, just so everybody can see exactly what we're doing. Okay, so we're going to have the shape column. We're going to have our area column. The units here will be millimeters squared. We got our y tilde column, units of millimeters. And then finally the product, y tilde times a, which is millimeter cubed. Now I've got three rectangles here. All right, so I'm going to look at each one separately. So let's do this one first. So let's draw it out here. So this is shape 1. Notice that's 8, and then the height here is 50. Okay, so what would be the area for that? Well, it's going to be 8 times 50, right? So that's 400. Now y tilde, does everybody remember what that is? Y tilde is the distance from a reference line to the centroid of each individual shape or region. Okay, so I'm just looking at this. So the centroid for this, since this is just a rectangle, would be right there in the middle, right? Now I want to pick a reference line. Everything we measure like this is going to be from the reference line, and I usually like to go from the bottom line here. So that'll be my reference line. So I want to go from the bottom up halfway. So if the total length here is 50, then that's going to be 25, right? So that's what that y tilde is. And then this last column, easiest column, you just take these two numbers, multiply them together. All right, so that's going to equal 10,000. Now let's go ahead, let's go down to this bottom one. Let's call it section 2. All right, so we have that blue region. Now this one's kind of tricky, right? Don't go ahead and put 50 here because it's not 50, because we already included this region right here, up here. So we need to take off 8 millimeters for this one, 8 millimeters for that one. Okay, so that's 16 that we're going to take off. Okay, so we're going to have 50 minus 16. Okay, so we got that, and then the height is 8. All right, so now let's see, what's 50 minus 16? What do we think that is? 34, right? So now what we're going to do is we're going to find the area here. So we're going to have 8 times 34. Well, what's that? Let's calculate it. 272. Okay. So now what would y tilde be? Well, we're going to the centroid of this little blue region. Okay, and we're going to measure from the reference line. So if the height here is 8, I'm going to go halfway up, so it's going to be 4. So then this last column is just going to be 4 times 272. So let's see what that is. 1,088. All right, and then finally we'll do this region over here. All right, now this is just like this one, right? So like I said, there's other ways you could do this. You could combine these together. There's several different ways you can calculate this. Okay, so we get 8 times 50, it's 400. And then y tilde is going to be the same thing, 25, right? Because we're going to the centroid halfway up is 25, and then the product here is 10,000 again. Okay, so we got this filled out, so now we're going to sum up this last column, sum up this second column. All right, so this will give us our total area. So our total area is going to be 1,072. And then over here, we got 10,000 plus 10,000, so that's 20,000 plus the 1,088. So 21,088. All right, and that's your sum of the products there. So now I'm wanting to find y bar. Okay, so y bar is basically the sum of the products over the sum of the areas. Alright, so let's do that calculation. And if we do that, what do we get? We get 19.67, and that's millimeters. Okay, so this would be part of your answer for part A. Okay, so basically to get up to this centroid right here, that's our y tilde, that's, hit the camera, is going to be 19.67. Okay, so that's what that information there gives you. Next, we got to find moment of inertia, and we have to find moment of inertia because we're going to need that to do the section modulus. All right, so let's go ahead and find moment of inertia. Okay, so I'm going to make the table again, and once I do that, I'm going to be out of room on this page. So we got our shape, we're going to have the moment of inertia, and then we're going to have the area again, our distance d, and then we'll have the I plus AD squared for the parallel axis theorem. All right, so we're going to have the same shapes, so we can just bring those down. And then let's fill this out. Okay, so shape 1 is this left side. Now this is a rectangle, so you're going to use the equation for the moment of inertia for a rectangle about the horizontal axis. So in this problem, we're calling it Z, right? So in your centroid or inertia tables, that's probably going to be called X. So we're going to have 1/12 base times height cubed. So if we plug in our numbers, we got 1/12 times 8 times 50 cubed. All right, and then notice your units here will be millimeters to the 4th. Okay, so let's see what we get for that. So it's 83,333.3. All right, area we already calculated up here, so just bring that down. And then D. All right, now that we've got the centroid, D is pretty easy to find. Okay, so D, what it basically is the distance between the centroid of the region, right here, this little C, and centroid for the whole body, which is right here. So it just wants that vertical distance there. It's hard for me to show you on here because of where I've written everything. But that's all it is. And the easy way to do this, if you have the centroid information, is to just take the y tilde, the y bar, find the difference, and then you're done. Okay, that's the easiest thing. It doesn't matter if it's positive or negative because we're going to come over here and square it, right? So it doesn't matter which order you do it in. Okay, so let's just do 25 minus 19.67. All right, so that should be 5.33. And then we come over here, you're going to take this plus A times D squared. So we'll write this one out. All right, and then you should get 94,689.89. Okay, and then we're going to do the same thing for the other two regions. All right, so this is 34, this is 8. So moment of inertia, still 1/12 times the base times the height cubed. All right, and now what are we going to get? Well, this is going to be a smaller number here. This is 1,450.67. Area, we already calculated, 272. Just bring that down. D, so remember what D is. If we come back up here, D is just going to be this distance between those two lines, right? Between the 2 points. So imagine a horizontal line going through this centroid, and we got a line going through this centroid. You want to find the distance between those. That's D. All right, so let's do 19.67 minus 4. Remember, order doesn't matter because, you know, we're going to square it, right? So it doesn't matter if you get a positive or negative here. So that's going to give you 15.67. And then over here, we've got this sum. All right, so let's write that out. And then that is going to give you 68,253.96. Okay. And then lastly, that right-hand section. So it's 8, that's 50. Let me move this up. There we go. And then your I is going to be the same, because basically the same shape. So let's put that there. So it's the 83,000 number. A is going to be the same. D is going to be the same. And then, you know, this right here will be the same. Okay, so that one was easy, right? You didn't have to calculate anything. And then finally, let's sum up this last column, and then that is going to give us our moment of inertia. All right, so if we sum all of that up, let's see what we get. Let's see. So 257,634. All right, that's what I got. And units there would be millimeters to the 4th. Okay, so that then is the second part of part A. Okay, so we found y bar, we found I. Now we have to find the controlling section modulus. Okay, so let's do that next. Now, the controlling section modulus, what we're going to do for that, first of all, let's remember what that variable is. That's that capital S, right? So it's the capital S, and where it comes from is this equation right here. So remember sigma allow, remember sigma is your stress, is equal to MC over I, right? So we've got that equation, flexure formula, and basically the section modulus just uses this equation, all right? So we could say it's M max over sigma allow, which then, if we solve again, could also equal I over C, all right? And this section modulus, this is used to help design beams, help you pick the correct dimensions and everything. If you look in the appendices of a mechanics and materials book where it shows all the beams, you will find an S column. All right, and this is what it is. So basically, we're going to have the ratio of I over C, and that's what we'll be using for that section modulus. All right, so let's go ahead and see what we should do here. Now, this C, remember what C is. C is your distance to the edge of your body measured from the neutral axis. Okay, so if we were to draw this representation, right, and let's say this is C, then our neutral axis is going to go through here. Remember, at the neutral axis, the stress goes to 0. This is the dividing line between where we have tension and compression when we've got a bending moment. Okay, so either on the top or on the bottom, you know, one of these is going to be tension, one on the other side would be compression, or vice versa. Okay, that neutral axis is that dividing line. And then C, that distance C, is measured from the neutral axis to the top or the bottom of the body. Okay, so let's go ahead and let's calculate that. So we want to figure out what our limiting section modulus will be, because that's what it's asking for, right? So the controlling section modulus. So let's do that first. So let's calculate section modulus for the top section. All right, I had to get some paper here. Okay, so we've got this. So let's draw this out again because I'm running out of room. Okay, that's our neutral axis. Okay, so let's find this distance right here. So let's say that's C. So this will be for the top part. So let's see what the section modulus is for this top region. And then we'll see what it is for the bottom region. And then we'll see which one is going to be the limiting factor. Okay, so S for the top, we're going to have the moment of inertia, right, which we already found, over C for the top. Okay, so we take our moment of inertia, which we just found, that 257,000 number. Let's put our units, and then we're going to divide it by C. Okay, so let's remember our dimensions. This total length here is 50 millimeters, and the neutral axis goes through the centroid. So we already found that to be 19.67, right? So C then is going to be 50 minus 19.67. Right, and that's going to be millimeters. So then when we calculate this, let's see what we get. Okay, so that's 8,494.35. And that's millimeter cubed. Okay, so that's what it is for the top. Now let's look at the bottom and see what we get for that one. So we're going to have I over the C distance to the bottom. Okay, so this was C top. This right here will be C bottom. All right, oh, and inertia doesn't change. And then for the bottom, what are we going to have? We're just going to have that 19.67, right? Because that is the distance from the neutral axis to the bottom of the beam there. So we get 19.67, that's millimeters. And let's calculate that. Whoops, 0.7. Okay, so that is 97.8, and that's millimeter cubed. Okay, so now we've got these two values. Now, which one is the controlling one? All right, so which one is the limiting factor? All right, well, basically, if you think about what the section modulus is, the section modulus, the bigger it is, it's more of an indication that your beam is going to be able to handle a greater load. All right, so you're going to have stronger beam when we have a bigger section modulus. So if that is the case, then our limiting section modulus would be the lower number because it's not going to be able to handle as much of a load. Okay, so we're going to pick the smallest number for the controlling section modulus. All right, so that 8,494.35, that will be our controlling section modulus. And let's just put, because it can support less load. And now we've got that. Okay, so that would be our answer for that one. Now, that's the end of part A finally. It took us a long time to get there, right? Almost 20 minutes to get there. Now let's do B. B and C will be quick. So B, it wants to know, let's move this down here again. B wants to know the bending stress right here at H. Right, I've kind of drawn all over it, but it's at the top of the little blue region right here, so it's kind of like right here. So it wants to know bending stress, and then it wants to know if it's in tension or compression. Okay, so let's go ahead and find this. Now the equation we're going to use for this is sigma equals negative my over I. All right, so now we've got this. And let me draw this back out again. Okay, now let's figure out what to do here. So we're going to have the negative sign. M is the bending moment. Well, that was given to us, right? That was given as the 375. Okay, so we can put that in there. And that was Newton meters. Right, always important to put your units. Okay, now what would Y be? What do we think? Let's draw this little picture a little bit better. Okay, so it looks like this. B is right here. Or not B, I don't know why I called it B. We're on part B, but we're looking for H. All right, so let's change that to H. Okay, so there's H. Now, what Y is the distance from the neutral axis, which is right here through the centroid, to H. Okay, so this is going to be Y. All right. Now, if we're below the neutral axis, we're going to say it's a negative Y value. If we were above it, we would say it's positive. So here, this distance, Y, is going to be essentially, well, let's put a bracket here. Negative, and then we're going to have 19.67 minus the height here, which was 8. Okay, so let's put 8 there. And notice these are millimeters. Okay, so now we've got this. So this is going to be like negative 11.67 right here for the Y. Okay, now do we notice a problem with the units? We do, right? We got meters over here, we got millimeters here. I got to convert something. So let's just go ahead and multiply everything by 1,000. All right, so basically we're going to convert this over here to millimeters. Okay, so that will get rid of that. And then now we're going to divide by I. I is easy, right? We already found that, so we just plug in that value we already found. So 257,634 millimeters to the fourth. So our units look good now. Everything is millimeters here. And then we can go ahead and solve. Notice that this and this are going to cancel each other out. The two negatives cancel. It becomes positive. Right? So we're going to have a positive value. And it's going to be about 16.99, all right? And units here would be megapascal. Now, since it's positive, that means it's in tension, okay? So if we would have gotten a negative, it would be compression. And that makes sense if we go back and look at what the moment is doing, right? So remember, H is down here. We've got that neutral axis, right? Here's that neutral axis. So kind of like up in here somewhere, right? And look at the moment, right? So it's going this way. So the moment here is pulling out on this bottom half, right? So below the neutral axis, it's pulling out, which is going to be a tensile stress. Okay, and that's what we get when we get this positive. Right, it's because that just the way the moment is, right? It's pulling out on that bottom surface there where H is, so we get tension. Okay, so that'll be T right there for tension, and then part C, we want to find the max bending stress. All right, well, max bending stress. For that one, what you want to do is we can use the same equation. Now the max stress is going to be either on the bottom surface or the top surface, right? So that's just your choice. It's got to be the top or the bottom. So what you want to do then is you basically need to find the y value that is the biggest. All right, so is the y value up on the top the biggest, or is the y value on the bottom the biggest? That's kind of what you have to figure out. So let's do that. So we're going to have negative m. M is 375. That's Newton meters. And then what do we think y should be? Well, let's look. Keep drawing this out. Right, so here we go, neutral axis. We know this is the 19.67. Now what's it going to be up top? Remember, the total length was 50, right? So what's that make this? So it's 50 minus 19.67. So that's 30.33. So which y value would be bigger? That one, right? So we're going to pick the bigger value because m and I aren't going to change. So y is the one that's going to determine the max value. Okay, so let's pick the bigger value. So we're going to have 30.33, and that's millimeters. Again, we got a unit problem here. Let's convert over so everything's in millimeters. Multiply by 1,000, and then divide by I. All right, so 257,634. Okay, now this one, go through and calculate. Notice we've got the negative, and the negative is not going to change. Okay, so we're going to have a negative 44.15 roughly, and that's megapascal. And we want to say if it's in tension or compression. Well, I already know by looking at the negative sign here that's going to be compression, right? So we could put 44.15 with the C outside of it. And then if you look at the actual picture of what's going on, you can see that it would be in compression because we're looking at this top section here. Notice the moment is going to be pushing into that top section. So that's going to be compression. All right, so we got compressive stress there. All right, and that's how you go about that. All right. So hopefully that made sense, and I will see you guys next time for a different problem. Have a great day.